are discussing the application of thermodynamics in two-phase equilibrium. And in my last class, the origin of the colligative properties of the dilute solutions have been discussed in terms of the more fundamental thermodynamical property called the chemical potential. Today, I like to discuss first colligative property, relative lowering of vapor pressure. Then I shall go for the other colligative properties like the elevation of boiling point, depression of freezing point, and osmotic pressure. And whenever I shall discuss the colligative properties, each colligative property will contain, or I try to discuss it elaborately, like what is meant by the property, what is the origin of this property. The property is explained in terms of these pictures and also by diagram, and what is the experimental law of this property, what is the validity of this law, and any sort of applications of this law, and how to show, and also to show this property is a colligative one, and lastly the derivations of this thermodynamical derivations of this colligative property, and with some problems with solution, so that the learners can get an idea fully about this property. We now start this P1 naught is the vapor pressure of a pure solvent at a temperature T. We know this P1 naught is a function of temperature only, and say P1 is the vapor pressure of the solvent in solution at the same temperature. And this P1 is a function of this temperature and also the X1. X1 is the mole fraction of this solvent in solution. So it is already known to us, and I can also show by means of this diagram that P1 naught is greater than P1, and this look, and P1 naught minus P1 is called the lowering of vapor pressure of the solution. And this lowering of vapor pressure is due to the lowering of chemical potential of the solvent when some solute is added to this solvent, and it is an entropy effect that I have discussed in my last lecture. So whenever this one is divided by P1 naught, means P1 naught minus P1 divided by P1 naught is called relative lowering of vapor pressure. Relative lowering of vapor pressure of the solution. And in short, I can write RLVP of the solutions. this is the property, and I can show this property is the colligative property of this dilute solution, and this property could be explained in this figure. In this figure also, this is the closed evaporated vessel in which the pure solvent have been taken at this temperature T. When at this temperature some amount of the solvent is vaporized and the vapor pressure is created, and the vapor pressure is determined by means of a manometer set in this container. Similarly here, in the same fashion, at the same temperature, solution have been taken, and the solute is non-volatile solute in a volatile solvent, and here the solvent will vaporize at this temperature and creates a vapor pressure which is recorded by means of manometer P1, and experimentally it is seen that P1 naught is greater than P1. P1 naught is greater than P1, means that there is a lowering of vapor pressure of the solvent when some non-volatile solute is added to this volatile solvent. So this is the colligative property, and this P1 naught is a function of temperature. P1 is a function of temperature, and x1 had the value of x1 greater will be the value of P1. So this could also be shown by means of a graph, and this graph, or this experimentally the vapor pressures of this one and this one could be determined at different temperatures, keeping the two solutions in a thermostat of a varying temperature. So this one could be experimentally determined as one, and not only that, the graph will be like that. Here the vapor pressure along the y-axis and temperature along this x-axis. So whenever we draw the experimental data in this curve will be like this, and it is the solvent, pure solvent, and it is the solution or solvent in solution. So at any temperature it is seen that if this one is a P1 naught, and then this one is a P1. P1 naught is always greater than P1. This curve could also be explained by means of a Clausius-Clapeyron equation. This vapor pressure increases with this temperature, but this variation is not linear. Actually, how the vapor pressure varies with temperature could be shown by means of Clausius-Clapeyron equation. Clapeyron equation, and the equation is ln P equal to minus LV bar divided by R into 1 by T and plus ln A. ln A is the integration constant, LV bar is the molar latent heat of evaporation, T the temperature, ln P the logarithmic of this vapor pressure of the solvent or any substance. So from this relations it is seen that with the increase in temperature, this vapor pressure will increase, but not in a linear fashion. If we plot ln P versus 1 by T, then it will give a linear plot. And also it is evident that with the liquids having the hard molar latent heat of evaporation, less will be the vapor pressure. It also could be written as P equal to A ln A is brought in the left hand side, and e to the power minus LT bar by RT. Means vapor pressure increases with this temperature in a exponential manner. So this colligative property, this property, relative lowering of vapor pressure, naturally depends on the concentration of the solution. Here the concentration, here will be the relative lowering of vapor pressure, and the concentration is expressed in terms of this mole fraction of this solute. Raoult's law of relative lowering of vapor pressure is the experimental law, and this law states that P1 naught minus P1 divided by P1 naught equal to X2, mole fraction of this solute in solution, provided there is some conditions. The condition is that X2 is the mole fraction of the solute in solution. This law is valid under certain conditions. Under certain conditions, the condition is that the solution must be very dilute so that it behaves ideally. Or we can say this relation is applicable only for the ideally diluted solution. And instead of writing this X2, we can write this N2 divided by N1 plus N2. So since 1 mole of any solute is equal to the Avogadro number of particles, so this property RLVP, it could be shown that it is the colligative property. As we can say, this one, the number of particles of this solute comparison to the relative to the total number of particles in this solution. So it is a colligative property, and this property does not depend on the nature or chemical characteristics of this solute. If we take different solutions of the same mole fractions, say sugar solution, say urea, glucose solutions having the same mole fraction, then the RLVP will be the same, does not depend on the characteristic properties of these molecules or the particles. So the validity is that it is valid for ideally diluted solutions, and the solute is non-volatile, and also in this case non-electrolyte. If this solute is electrolyte, then we shall discuss in a later stage while we shall introduce another term, vent of I factor. So this relation is the experimental relations of the Raoult's law of relative lowering of vapor pressure. Now we can see what if any application of this law could be obtained. This one we can write in short, delta P1 and divided by P1 naught equal to N2 divided by N1 plus N2. Instead of writing the mole fraction, we can write in terms of this number of moles. And you know, this mole fraction is the concentration of the solutions, and this concentration is temperature independent. So as long as the solution behaves ideally, this relative lowering of vapor pressure is temperature independent. Whenever the solution will not be ideal one, this property will depend on the temperature, and this relation will also not be applicable. So it is to be minded, it is to be taken to consider always this relation is valid for ideally diluted solutions, and solute is non-volatile and non-electrolyte. Since the solution is very dilute, so N1 is much greater than N2. So we can write this N2 divided by N1, or we can write this W2 divided by M2, weight of this solute in grams, divided by molar mass of this solute, and here it is W1, mass of this solvent, divided by molar mass of this solvent, or delta P minus P1 naught is equal to W2 into M1 and divided by W1 into M2. So this one could be determined. I have shown here this, if P1 and P1 naught could be determined by means of manometer, then this term could also be determined experimentally. And while we are preparing this solution, this W1 and W2, these are the mass of this solvent and solute, could also be known. And M1, if we know the M1, molar mass of the solvent, then M2 could be determined. So M2, the molar mass of this solute, will be equal to W2 into M1 divided by W1 into del P1 divided by P1 naught. So this is the application, and this is the application of measuring the colligative property of the dilute solutions. The molar mass of the solute could be calculated by determining the relative lowering of vapour pressure of these solutions and the composition of these solutions. And you know, the molar mass of a substance is very important. Unless and until we know the molar mass, we cannot calculate, we cannot find the molecular formula of that substance. So this one is the very important applications of all the colligative properties in relative lowering of vapour pressure. This is the formula. Now I set one experiment which is the Oswald-Walker method to determine the relative lowering of vapour pressure very accurately. Here one is a flask, round bottom flask. Here is another round bottom flask. Here contains the solution. Here contains the solvent of the solutions, and it is the U tube in which the anhydrous calcium chloride is taken. Anhydrous calcium chloride is a good water absorber, and here the solvent, we shall take this water. Water is a very common solvent. Variety of, it is the versatile solvent, and variety of compounds, variety of solutes are dissolved in water. Since its diuretic constant is very high, not only that, the water is easily available and very, very cheap. So here we have taken this water as solvent. Here the solution, and solution contains the non-volatile solute in water and also non-electrolyte. Here dry air is passed in this. Dry air is passed through this glass tube, and this one go through this solution first, and this dry air, whenever passing through these solutions, it is getting saturated up to the vapor pressure P1. Saturated with this water up to the vapor pressure P1. So there will be loss of mass of this flask, and loss in mass of this flask is M1. M1 is proportional to P1. Now this partially saturated, and then this air is passed through this solvent. Solvent is having the high vapor pressure P1 naught. So more water will be taken up from this plus and up to the saturation of this P1 naught, and there will be again loss of mass of this container, and this mass M2 equal to P1 naught minus P1 up to here, up to the dry air is saturated up to P1, and in this case saturated from P1 to P1 naught. So M2 is proportional to P1 naught minus P1, and all the water will be absorbed whenever passing through this U, and here the anhydrous calcium chloride, there will be gain in mass, and the gain in mass will be equal to M1 plus M2, and this is proportional to P1 naught. So the relative lowering of vapor pressure equal to P1 naught minus P1 divided by P1 naught means M2 divided by M1 plus M2. So this measuring the loss in mass and gain in mass, it is possible to calculate the relative lowering of vapor pressure of the solution, and which helps to calculate the molecular mass of this solute. This relation actually could be derived thermodynamically. Though Raoult formulated the experimental law, which is empirical law, but it could be derived thermodynamically by using the chemical potential. I have already shown in my last lecture that P1 vapor pressure of the solvent in solution is the vapor pressure of this pure solvent into X1. X1 is the mole fraction. So this has already been derived by using the chemical potential. So instead of P1 naught, instead of X1, I can write 1 minus X2, since X1 plus X2 equal to 1. So if we do this slight calculations, then it will be this P1 naught minus P1 divided by P1 naught equal to X2 mole fraction of this solute, and this is the Raoult's law of relative lowering of vapor pressure. And by rigid thermodynamical method, we can also show this one is a temperature independent, so long the solution behaves ideally. This is one problem set in National Eligibility Test at 2000. The problem is the pressure of benzene is 400 torr at 60 degrees centigrade. The vapor pressure of a 0.1 molar solution of non-volatile compound in benzene at 60 degrees centigrade would be 404 torr, 400 torr, 396 torr, and 4 torr. You can see this data. Some data are missing. Actually, the molar mass of this non-volatile compound is not given. Not only that, in terms of if we change the molarity to mole fraction, the density is required, density of the solution is required. So all these two data are not given in this problem. So the exact correct option of this problem has to be done by means of the guess or intuition. That we have an idea that there is a lowering of vapor pressure whenever non-volatile solute is added to the solvent. So here it is seen that first option, the pure benzene has the vapor pressure 400 torr, but here first answer is 404 torr, which is not possible as vapor pressure will not increase for the solution, and here this will not be possible as there is no change of vapor pressure while adding this non-volatile solute to benzene. And this one 396 slight decrease or lowering of vapor pressure of this solution. This is the correct answer, and this one is also not possible, that the vapor pressure of this solution is very, very low, which is not possible. So correct answer is 3. This is another problem set in GATE, Graduate Aptitude Test in Engineering, in the year 2002. This is a bright problem. The method by which we can calculate the molecular weight of this non-volatile solid. The vapor pressure of ethanol at 220 degrees centigrade is 44.5 millimeter. When 15 gram of a non-volatile compound A is dissolved in 500 gram of ethanol, the vapor pressure decreases to 43.5 millimeter. Calculate the molecular weight of A. So here the solution to the problem could be obtained by using the Lowell's law of relative lowering of vapor pressure. Say P1 naught minus P1 divided by P1 naught equal to X2. This is the Lowell's law of relative lowering of vapor pressure. Putting the values here left hand side, it is 4 P1 naught is 44.5 minus 43.5 divided by 44.5, and this one equal to N2 divided by N1 plus N2. For this one, we can write this minus this means 1.0 divided by 44.5 equal to N2 minus N2 by N1 plus N2, or inverting this one by taking upside down, 44.5 equal to this one N1 by N2 plus 1. So N1 by N2 equal to 44.5 minus 1 equal to 43.5. And this N1 by N2 equal to W1 into M2 divided by W2 into M1 equal to 43.5, or M2 molecular weight of this solute A equal to 43.5 into W2 into M1 divided by W1 divided by W1. M2 equal to this minus W1 divided by W1. So putting the values of 43.5 and into W2 is 15 gram, and molecular weight of ethanol C2H5OH, and so M1 equal to 46. So here 46 divided by 500 down. So this will give you this 60. So very easily this problem could be done, and the molecular weight of this solute A is found to be 60. This is all about the relative lowering of vapor pressure. Thank you all for watching this video, and I hope you will subscribe my channel if you like so. And in next class I will deal with elevation of boiling point, the second colligative property of this dilute solution. Thank you.